Cloud is all about choice. Take full advantage of multi-cloud with Couchbase, a geo-distributed, cloud-native data platform built to power your business-critical applications. Avoid cloud lock-in and open up a world of possibility. Start a revolution with Couchbase. Learn more at couchbase.com/cloud.
Hello and welcome to the InfoCube podcast. My name is Wes Rice and I'm the chair of the software conference called QCon and the new QCon.ai brought to you by InfoCube. QCon AI is coming up in a few days, and if you're a software engineer looking for patterns and practices of machine learning and how to apply them in your day-to-day, QCon AI is the conference for you. It's an applied AI conference for software engineers. Today, I'm speaking to one of our speakers, Danny Yuan. Danny is the real-time streaming lead at Uber. He's led Uber's first real-time time series forecasting pipeline. He's led a team to build and operate Uber's Jupyter Notebook service, and he's re-architected Uber's backend for real-time tracking. On today's podcast, we discuss real-time streaming architecture at Uber, including some of the design decisions, the trade-offs, and implementation details. In addition, we talk about the field of data engineering and some of Danny's thoughts on where we are today and where the field is going. Thanks for joining us. Danny, welcome to the InfoQ podcast.
Thanks for having me, Wes.
So what does it mean to be the real-time streaming lead at Uber?
Well, that title was used a long time ago. My team builds more than just a real-time streaming system. In fact, we use the real-time streaming platform provided by our infrastructure team. And what we do is to build an end-to-end analytic data platform for people to perform forecasts and tasks, and also for people to query data or perform OLAP type of queries in real time. The system can ingest data from Kafka almost instantly into our storage and make those data available for different people, for data scientists, for engineers, for management, and also for operations people to know the pulse of the city and to know the supply and demand or maybe health of different cities in a really, really fast way.
When we talk about in this architecture at Uber, what are we talking about as far as scale?
If you think about it, we need to know what's going on in every corner of the city as long as there's Uber services. And so we need to track how Uber's cars move and what kind of supply and demand is. And that gets translated into around 850,000 messages to 1.3 million messages per second into our streaming pipeline. And also, after we process them and store them, we store about 12 terabytes of data per day. And as for queries, we perform thousands and thousands of queries per second. It doesn't look much, but if you look at the number of documents scanned, it's actually reasonably large. And in normal days, the system scans around 100 million to 4 billion messages or documents per second.
Wow.
And that goes on almost every minute of the day.
And your team has 30, 40 people on it?
For this particular system, we have about 10 to 12 people. I lost count.
Nice. So what does this architecture look like? I know Uber is got like Node on the front end that receives all these things at kind of the API layer. And then you've got a lot of Python at the back. So are each of these services, each of these layers emitting events into Kafka and then you're processing from there? What's that architecture look like?
Yeah, that's pretty accurate. So Uber's front end are mobile phones. Right? We have driver app and rider apps. They ping or call our API layers all the time, and the API layers will ship this request to different services. We have a distributed service architecture, and all the services, and including the API services, will generate all kinds of events, and those events are shuffled into Kafka. Kafka is like our information highway.
Yeah.
And then our application will tap into Kafka to retrieve the events of our interest. And then the system will process those events on the fly. And the process results will be stored in an analytic database for which we use Elasticsearch. And then we build our federated query layer in front of the Elasticsearch to provide SQL-like OLAP type of queries. And then we build a visualization layer, we build our forecasting pipeline, we build our analytical pipeline and services, so on and so forth.
It's a Lambda architecture, right?
Yes, it has been a Lambda architecture, meaning that we have a streaming system that process data and store them. And we also have a corresponding batch pipeline for every single job so that if disaster strikes, then we can backfill. Or if we cannot generate accurate enough data on the fly, then we have a batch processing to augment generate data to make them more accurate, but with a significant delay. But over time, we realized that it takes too much time to maintain this kind of Roman writing-like system, because every single job or say every single piece of logic has two counterparties, the batch and the streaming. So we are moving towards a Kappa architecture, meaning that we have only one single stream processing for both batch processing and streaming processing, except that whenever we need to do any kind of batch processing, we just replay the events from our batch store, which is HDFS, into our streaming jobs.
You've got Kafka as this kind of information highway that's flowing through there. And what are you using to actually do the stream processing against that information highway?
We started with Apache Samza. Internally, we call it Athena. The infra team provided Athena or Apache Samza as a platform. They build all the bells and whistles and tools and ecosystem around it. So we use that. But over time, we also find more complicated or more involved use cases. Therefore, we have started to move everything to Apache Flink.
Why are you moving to Flink?
Well, the reason is for more sophisticated event handlings. In particular, we have quite flexible windowings. Sometimes we have event-based windows. Sometimes we have trigger-based windows. And a lot of these time windows are based on event time, not processing time, which Apache Samza is not that easy to use to handle this kind of situation. And also the state management and checkpointing of Flink is quite nice to use.
If I remember right, the programming model is supposed to be pretty nice too, right?
Its programming model is really nice. It's a data flow-based programming model with built-in support of all kinds of key-based windowings. So writing this kind of logic becomes easier. And another added benefit is if I want to write a topology or a job that involves multiple tasks, multiple nodes in Samza, I have to create multiple Samza jobs. So maintaining them can be a little bit laborious. But in case of Flink, it's really just one single job. Flink will figure out how to deploy this job into a distributed fashion. So it saves us a lot of time too.
You talked about event time and processing time. That's an important distinction with Flink. Can you talk a bit about that?
Event time refers to time when an event happens. Let's say some rider requests a car. At the moment the request is made, then an event time will be attached to a particular request event. The processing time refers to time when the event reaches the stream processor and is ready to be processed. Then there's another time. So usually there's a delay. Then in this type of world, our challenge is we don't know how much delay an event will be. Sometimes there's no delay at all, and that's the happy case. Sometimes there's a little bit of delay, but sometimes there could be a lot of delays. Then now we need to answer these kind of questions. If an event is really delayed, should we drop it or should we add it into already calculated results? Or how do we know that the event is already delayed? And for all these kind of questions, Flink provides mechanism for us to answer.
So Samza doesn't have that same capability?
Well, Samza can provide some of the capability, but not that conveniently. If you look at Samza, its strength is it's really simple. It essentially provides a few APIs, a handful of APIs. The key API is process a message. You process a message, you get an envelope. The envelope has the content of the message, and also it has all the metadata of this message. And that's pretty much it. And also you have a timer, and you have some kind of state management support. But that's it. And if you want to do anything like windowing or some kind of more sophisticated processing, then you have to build your own mechanisms.
What about with Spark Streaming? You started down a Spark Streaming approach too, right?
Yeah, so before Apache Flink, we need to generate sessionize the data. And generating sessionized data involves processing more than 10 different data sources, and also involves maintaining different kinds of time windows and a state machine inside memory. And this state machine needs to be persistent so that if the job goes down, then we can recover the state machine because you cannot lose session data. And so in that case, using Spark Streaming seems to be a better way of building this. That's how we started with Spark Streaming. But we used that only for a few jobs. And then Apache Flink came out and the version seems really powerful. Then we started migration immediately. But that's before the structured streaming came out. But since the company has moved to Flink, so we stick with Flink too.
I see. So you mentioned that it's a Lambda architecture, so that implies that there's batch as well. What are you processing the batch jobs with?
Usually we create a counterpart for each individual streaming job. Let's say I have a streaming job that generates sessions in real time or on demand. Now, or in streaming fashion, that's what I mean. Now, if I find that there's a bug in my code for the last 3 hours, so that means the 3 hours, the data generated in the last 3 hours is not that useful anymore, right? Then I need to backfill the data. Then I have to have a batch job in place. So that's the batch part.
I see. So there's a one-to-one matching between the two.
That's right.
What do you use actually? Do you use Flink to do your batch processing, or do you use Spark?
We use Spark.
So why Spark and not Flink? Why two different?
When we started, there was only Spark. And also because Spark is widely used for all kinds of batch processings, it's well integrated with the Hadoop ecosystem. And also the company has built a large number of tools, profiling tools, and debugging utilities, monitoring, so on and so forth, right? The entire ecosystem is there. So it goes way beyond than just a single technology. That's why we're still using that.
I want to shift gears just a bit and talk about how you're using Elasticstack.
Mm-hmm.
You use Elasticsearch a bit differently. Can you talk a bit about the role Elasticsearch plays at Uber?
We are not using that as a search engine. Instead, we're using that as a single table OLAP store that supports time series processing.
So a single table OLAP store that supports, we're talking Elk Stack, right? The thing that you collect logs with and visualize and look at your logs. Mm-hmm. You're using it as a NoSQL data store for OLAP queries?
That's right. Well, and we're not using the entire Elk Stack. We only use Elasticsearch. We didn't use Logstash. And we have our own visualization layer and query builders. So we're not using Kibana as well.
Why? What made you choose Elasticsearch as your NoSQL data store?
I wouldn't even say it's NoSQL. It's really just it's an online analytical processing store. The reason is usually if you look at our data usually has multiple dimensions. It has many dimensions. Some of them are numbers. We call it metrics or values, numeric values. And some of them are really textual values. So those are dimensions. So such as product types and such as the state location. And also we divide up our cities into grade system. And so each grade has a unique ID. That unique ID can be a dimension. And maybe this type of trip can be a dimension. And for, let's say, trip status, and if the trip is completed, the status completed is another dimension. Our largest table actually has hundreds of different dimensions.
Interesting.
That's why it's very important for us to be able to apply arbitrary Boolean filters. If this dimension is equal to that value, but that dimension is not in this set of value, that kind of Boolean queries. And if you want to do efficient Boolean queries, plus group bys, plus aggregations, then all of a sudden you don't have many choices, and Elasticsearch happens to fit the bill.
So just to back up for a second, you've got these events that are emitted from your architecture. They go into Kafka. Mm-hmm. You've got kind of a Lambda architecture that's moving to a Kafka architecture that you're using streaming, like Flink streaming, to be able to process and do feature work. And then it's stored in Elasticsearch with kind of high cardinality so that you can do a variety of different searches. And I guess you're using the high-speed search capability that Elasticsearch offers to be able to get this real-time data processing. Is that?
Yeah, well, it's not entirely accurate. We're not using the high-speed on search side. Of course, the indexing will be in play, but Elasticsearch actually has its own data structure to support query capabilities or to support aggregations. The data is called field data. It's mostly stored in the memory and then mapped into disk. It's a Elasticsearch specific version of columnar store. Elasticsearch will perform all kinds of aggregations on that data, and it leverages the indexing structure for Boolean queries.
Very nice. All right, so let's talk a bit about this. When I was reading kind of the introduction, I talked a bit about how you're a part of the team to build this first real-time time series forecasting pipeline. Mm-hmm. So I want to break this down in the context of what we just discussed and kind of talk about what all this means. So first, real time. When you say real time, how quick are you getting this data into your system?
Real time is a overused term. It's more like a marketing term now. But I would say we're capable of making, and especially for forecasting, because you're forecasting into the future, right? If you can forecast accurately into the future in an hour, then that means any data in an hour will be available to you. So there's no delay at all, right? So in this case, the real-time part is about retrieving the most recent data and then perform this kind of forecasting as fast as possible. And usually our granularity is in the range of minutes, which means we can grab, let's say, the last 10 minutes of data and also the historic data of, let's say, last hour, last 2 weeks, so on and so forth, combine them and then make a accurate enough forecasting into the next hour or even into the next 24 hours or maybe next week, depending on our use cases.
Time series forecasting. So if I think of time series forecasting, I kind of think it kind of like this simple example where if I have 1, 2, 3, 4, 5, it's going to be able to give me 6, 7, 8, 9, 10 as a forecast on some interval. Is that accurate, what we're talking about?
Yeah, it's most accurate. Well, in the particular example you give, you're talking about a single variate time series, meaning that you only have one value.
Right.
So in our case, eventually it boils down to this single variate time series. But our challenge is usually our data is multidimensional, and also we want to know in a much smaller region what's going to happen. And in a city, usually there are many these kind of regions, right? Tens of thousands to be for on average. So how do we perform this kind of forecasting for so many time series in one single shot?
Can you give me an example? I mean, is this like how many cars to place in a given region in the next hour? What are some of the use cases that you're using for the forecasting solution?
Yeah, for example, we want to predict supply and demand. We want to know if the marketplace is balanced or if there's any kind of local hotspot for demand or supply. First of all, we need to model supply and demand. It's really hard for us to use the number of cars or number of riders, because number of riders may not be active. Number of cars may be busy taking riders already. So in that case, we have a pretty elaborate model to describe how to model supply and demand should be. And then we have this system to calculate the supply and demand. And then we forecast those numbers in each individual region.
What do your models look like?
We have multiple models. So usually we even have competing models. Usually we start small. For example, our first model is based on fast Fourier transformation. So it's based on smoothing. We also have regression-based model. It's generalized, a general linear model. We also have like RNN-based, deep learning-based models. And we also have tree regression-based models. And we even have the really interesting one, Kalman filter. So we have filter-based models.
So you said sometimes you've got them training, sometimes you've got them competing, sometimes you've got them out. What is this, I guess, the pipeline look like for our building, training, and deploying models?
The pipeline is similar to most of the pipelines on the market. So we started with raw data, or let's say the data stored in HDFS. We need to process them. We call it feature engineering, because essentially we need to extract the data that we need to use and also the dimensions of our interest. And then we need to organize them into some kind of format that's easy to be consumed. Usually the format is conceptually similar to a data frame. And then with this kind of data, then we deploy our training models. The training models will run periodically if it's a batch-based one. We don't have any online training models. Probably in the future, we are going to have them. And in that case, we get data, we feed data into our models to train them. Once we get our model, the model will be stored in the model manager so that we can track which model we use, how good they are, so on and so forth. We also have a serving layer. The serving layer can automatically discover which model is ready to be used. And then we can take in incoming request and return the forecasting. And what we also have scheduled the forecasting. The forecasting can run from time to time so that, or can respond to events so that it can generate forecasting results. The forecasting results will be stored in OLAP store so that people can query them and also can visualize them on a really nice web tool. And we also have validation layers that take the forecasting results and also the real results and historical results and compare them to make sure that this model is working as desired. And if the validation is, the result is not so good, we also have a way to automatically switch over to a previously working model so that we don't get affected.
And all of this pipeline management, is this custom software, or are you using something to manage these model deployments?
We build our own. I'm not aware if there's any open source version, partly because it's highly specific to our use cases. Maybe there could be some generalized version, but since we just started not long ago, we really want to have something working in production, test the water, gather enough intuition, and then worry about generalization.
How are you building all these models? Or is this Python? Is this Scala? Are you using something like TensorFlow? What's the platform these things are written on?
We do have TensorFlow deployment. TensorFlow deployment is actually nice, right? Because that means the data scientists can write their models and directly deploy them into production. But before that, we didn't have that, and there is a gap in there. Data scientists will use their favorite tools. Usually it's part of a SciPy ecosystem. They use pandas for data processing, and they use NumPy, and also they use scikit-learn for their modeling work. Once they verify that their work is valid and is ready for production, then engineers need to somehow translate their code or their models into production code. It could be PySpark code, it could be Java code, or it could be just a wrapper around their modeling code. And so it's pretty ad hoc.
I see.
It works for a while, it's still working, but then we're looking for new ways to make it more efficient.
So what is the unit of deployment? Do you package these into containers, or how do you get these things out into your infrastructure?
Yeah, we package them into containers, and we have a deployment tool. So we deploy them into our general service clusters.
I see. You mentioned the data scientists build this. What does the team structure look like? Do you have data scientists embedded with your teams, or do you have a special group that's data scientists and then another team that's data engineers? How do you divide and break that up?
We have data scientist organizations, but then the data scientists are embedded. Well, I wouldn't say embedded. They work closely with engineers, so engineers and data scientists form a small group to attack like specific forecasting tasks, or let's say any kind of modeling work.
What are the roles that you have?
Really just data scientists and engineers.
Okay.
Data scientists build models, analyze models. Engineers build models, productize models, and also build tools. And I cannot stress enough about the importance of building tools. I even venture to say 80% or even 90% of work of great machine learning engineers is about building tools to support modeling, to support the entire pipeline, to make sure that people can iterate fast enough. It makes a huge difference between deploying a model and every 3 months or every 3 days.
A lot of engineers think of machine learning as kind of a black box, that it is kind of the field for data scientists and they don't want to get involved. What are your thoughts about that?
I think that we need to change this kind of thought. I would say machine learning is a great tool. It's a set of toolbox, and it would be great that software engineers can master this kind of tool so that it can even apply them for different use scenarios. One example is we have hundreds and hundreds of knobs in a complex system, like in database or in Elasticsearch. And some people have already figured out a way of using machine learning algorithms to automatically tune the system. So it's a great application, and it doesn't have to be done by just data scientists. It can be done by software engineers too.
Yeah, absolutely. Bayesian optimization to do JVM configuration parameters, for example, like at Twitter.
Yeah.
There's all kinds of use cases that you can apply just machine learning into your day-to-day work if you think it through. Yeah, it's very cool.
Yeah.
So what do you recommend? We'll start to wrap this up. What do you recommend for software engineers who want to adopt more machine learning practices on how to move forward? And feel free to say QCon AI.
QCon, yeah, for sure. Yeah. Start with the conference. In addition to conferences, I would say just start doing and learning. Without output, you really don't have input. Reading alone doesn't really give you much. You may learn about 10%, 20%, depending on different people, but certainly not 100%. And also, my personal experience is don't be afraid. I can share the same experience. It was back in 2011, so Netflix invited Andrew in to give us a talk about deep learning. I remember those slides, right? The slides had pages of formulas and equations, and I thought it was really too hard for me. But it turned out it's not true. All those math symbols and formulas They are college-level mathematics that anyone who's willing to learn can pick up relatively easily as long as you put enough time. And the good news is you don't have to start with math or theory. You start with intuition and practice. And so you practice, you apply some machine learning tools, so you use the existing one, well-boxed one, maybe start with scikit-learn. And then over time, you may ask questions, like how do I apply this? What's the limitation of my tool? How do I tune the parameters? Or maybe, hey, here's the new idea from this new paper, but it's full of math. How do I read it? And then you set up to learn more math. And it turned out once you have drive and specific needs, it's like a laser-focused area. Right? Then you can go there and then make all the connections. Everything becomes relatively easy. And another one is I would encourage people not to stop at using the tool. If you only use the tool, you only know what is there, but you don't know why it is there. And certainly you cannot pick up new knowledge from papers. And that will be limiting as well. So don't self-limit yourself and start an iterative process, start doing something, and then learn a little bit theory and rinse.
I don't know how else I could wrap it up. Danny, thank you for taking time to chat with us today.
Thank you. It's great talking to you.
Good day, I'm Shane Hasty, and I'm the host of the InfoQ Culture Podcast, a software engineering podcast that looks at team leadership, product ownership, and a wide variety of culture-based topics. We've had recent guests, including Rich Murnov on product development trends, Wendy Clausen on mindfulness and effective communication, and Harsh Sinha on building culture at TransferWise. If you're in a leadership position or aspiring to get there, you might want to check it out. You can download and subscribe via the same place you found the InfoQ podcast, or find out more at infoq.com/podcasts.